Now that we have some practice working with Laplace transforms, let's talk about how to actually use Laplace transforms to solve differential equations. So the first thing I'd like to do is just recall our definition of the Laplace transform. So we indicate the Laplace transform with this capital L, and the input is a function of t, and what the Laplace transform is this integral from 0 to infinity of e to the minus st times our function f of t dt. Okay, and so for the output we get a function of s. And so in the previous two lectures, we actually developed several formulas for common Laplace transforms, so we recorded some of these here in this table. And we're going to definitely make use of this today. But there's actually one more formula that I need. And so differential equations involve derivatives. So one thing I would love to know is, well, what is the Laplace transform of the derivative of some function f? Is there some nice formula for this in terms of, perhaps the function f itself? Okay, well, how do we proceed? Let's write down this definition. Okay, so instead of f of t, I need to put f prime of t dt. Okay, well, we could stop there, but this is not really telling us much, right? But whenever I see a derivative of a function times something else inside an integral, I think about integration by parts, and that's because integration by parts turns an integral like this, u dv, into, well, uv minus an integral like this. So we can at least try to rewrite this integral using the integration by parts formula. And if we have limits here, then we have to be very careful here. We have to evaluate this at the limits. Okay, so let's apply integration by parts. Well, what is my u and what is my dv? So my u here is going to be, this is the thing I want to be the dv, actually, this f prime of t dt. That's that's dv. You see, I can now express this integral here in terms of v, which is f. And that means that this part is going to be my u. And so what do I get? I get uv, which is e to the minus st times f of t, but evaluated at the limits, infinity and 0. And we know what it means to evaluate at a limit of infinity. It actually means a limit as b goes to infinity, and then we evaluate it at b. But I'm just going to write this to save space, and then we have minus, right, minus sign in the integration by parts formula. The integral of v, which is f of t, du is minus s times e to the st. So I'll take out the minus s, and I have e to the minus st dt, like that. Okay, and what is this here? So let's do this part first. Well, if I evaluate this at infinity, as long as f of t does not grow too fast, this is actually going to be 0. We have a problem if f of t is something like, say, e to the t squared, right? Then this is actually not going to be 0 when I plug in infinity for any values of s, in fact. But we're assuming that this f of t that we have here is not growing too fast, essentially. So we actually get 0 when we plug in this limit here. And then when we plug in 0, well, what do we get? This part just becomes 1, right? So we get f of 0. Okay. So this actually just becomes f of 0, but it's minus f of 0, right? Because it's this evaluated at the upper limit minus this evaluated at the lower limit. So I get minus f of 0 and then plus s times, well, what is this right here? I'm sure some of you recognize that this is just the same as that, right? So it's just the Laplace transform of f, right? F of t, not f prime. Okay, so we now have a formula. This is a really important formula. So I'll say this is a key formula almost that we're going to use. We can actually express the Laplace transform of a derivative in terms of the function itself, the Laplace transform of the function itself. So this is s times the Laplace transform of f of t minus f of 0. Okay. Let's go ahead and box this. Okay. Well, one other thing that we're going to need, so we've solved some second order differential equations, and we'll probably want to do that again today. What about the second derivative? Well, we don't need to do this whole thing with integration by parts again. We can just apply this formula. So what is this going to be? It's going to be s times L of, well, here I need to put f of t, right? The antiderivative of f prime. Here the antiderivative of f double prime is f prime. Right? So I'll put f prime, and I have minus f prime of 0. Let's use this formula again, right? I still have a Laplace transform of a derivative. So this is going to be s times L of f of t minus f of 0. That just came from this bit here. And then I have a minus f prime of 0. Okay. So then this becomes s squared times L of f of t minus s times f of 0 minus f prime of 0. Okay. What if I wanted even higher derivatives? Well, we do the same thing. Right? So we can even try to say in general, what if we have a an nth derivative? So a common notation for that is an n up here in parentheses. So that means the nth derivative. Just make a note of that. Okay, what's the Laplace transform of this? Well, can we spot the pattern maybe? So here we have an s times L of f of t. We have an s squared times L of f of t, and then minus an s, and then this continues. So it turns out that what you get here, and you can prove this by induction, well, what power of s do you think you get? It's s to the n times L of f of t. Let's write out the next term too. And you get minus, well, the s's go down by 1. So s to the n minus 1 times f of 0 minus s to the n minus 2 times f prime of 0, etc. And you keep going until we get, well, let's go down to s to the 1. So what derivative are we on? Okay, we went from n minus 1 down to 1. So here we're going from the 0th derivative, I guess, up to the n minus 2 derivative of 0. So take n minus 2 derivatives of f, evaluate it at 0. And then what's our last term going to be? Well, it's going to be the n minus 1 derivative. Again, evaluated at 0. Okay. All right, great. So let's now actually, I'll give you a quick problem to try, just to get used to this formula. So here's the problem. Given that, okay, the Laplace transform of sine of AT is, well, remember what we got last time, it was a over s squared plus a squared. So let's say we're given that. Find the Laplace transform. This is kind of a fun little problem. We already found a Laplace transform of cosine, but this is just some practice using the formula. So find the Laplace transform of cosine AT using this formula, using the boxed formula. Okay. And we know what the answer should be. The answer you should get is this one, s over s squared plus a squared. But the idea is to use this. And we can use this because, see, cosine is the derivative of sine. And so that's sort of exactly what we have here. You have to be a little careful with the a, but try this problem. And with that, let's actually just start solving differential equations. And so I'd actually like to start with an example. We'll sort of discover the method through the example, then I'll outline the method, and then we'll do another example or two. So here's a first example, let's say. First example. Let's solve. Let's start with something familiar. So let's solve the initial value problem. Maybe all the examples from today will be equations that we could have solved using previous techniques, and we'll start doing some more complicated ones next time. Okay, so here's the initial value problem. Let's do a second order linear differential equation with constant coefficients. And I'm going to give some initial conditions. Y of 0 is 1. Y prime of 0 is 0. Okay. Well, like I said, this is one that we've seen before. How would we solve this? We would guess e to the RT. We would look at the characteristic polynomial, determine what the roots are, whether they're 2 real roots, 2 complex roots, or 1 repeated real root. And then we'd proceed from there. But we're actually going to do something completely different. So the idea is actually we're going to take the Laplace transform of this differential equation. So I'm going to do this. I'm going to take the Laplace transform of both sides, of course. I can't do something to one side and not to the other side. So I have L of 0 here. Okay. Well, I can use linearity of the Laplace transform. It's another very important property. Okay, and I have minus L of y prime minus 2 times, again by linearity, L of y. That's going to be L of 0. Well, what is L of 0? That was sort of our example 0 from last time. That's just 0. Of course, because when you plug in 0 here, that just makes the whole integrand 0. Okay, now do you see what we're going to do? We're going to use our key formulas. Okay, so here's the first one. Let's actually box the second one too, because we're going to be using this whenever we see a second order differential equation. So yeah, again, this was L of f prime of t, f double prime, sorry, of t. Okay, so let's use this formula to rewrite L of y double prime in terms of just L of y. So this one here becomes, well, it's s squared times L of y, right? Minus s times, what do I put here? I put y of 0. and then minus y prime of 0. Interesting. So these are actually going to be our initial conditions. We actually need initial conditions to use this Laplace transform method. Okay, so we need an initial value problem. It's kind of like Euler's method, how we needed initial conditions as well as the differential equation. So that's that part. And then this part here, so we get minus L of y prime. We're going to use this formula here. S times L of y minus y0. I need to put it in parentheses. You have to be careful with all the minus signs. Okay? And then finally minus 2 times L of y. And that's going to equal 0. Well, what are these things? So y of 0 in our example is 1. And here we have it again here. And this y prime of 0 is just 0. So we have s squared times L of y minus s times L of y minus a minus 1, so plus 1. And then we have minus 2 times L of y. And that's going to equal 0. Okay. Now what? So do you see what we're going to do next? Well, we see that there are several L of y terms here. So remember, my goal is I want to find the function y of t, right, that satisfies this differential equation, that solves the initial value problem. There's that function, right? I actually have this in terms of L of y, but I'll solve for L of y. So I have s squared minus s minus 2 times L of y minus s plus 1 equals 0. Okay. Let's move this over to the other side. Equals s minus 1. And now I just divide by this. So I get L of y equals s minus 1 over s squared minus s minus 2. Okay. That's L of y. I want y. So what am I going to do next? Well, I'm going to take the inverse Laplace transform. Okay, so let's just write our ideas here. So here we solved for L of y. Here, to go from here to here, we just took a Laplace transform of the whole differential equation. Now finally we're going to take the inverse Laplace transform. Okay, how do we do that? So this doesn't look like anything from our table, but we notice that we can factor this denominator. It's s minus 2 times s plus 1, it looks like. Okay, and then let's try to break this apart into two fractions. One with the denominator of s minus 2, one with the denominator of s plus 1. Okay, so when I multiply this one by s plus 1 over s plus 1, I get this in my numerator. Now when I multiply this one by s minus 2 over s minus 2 to find a common denominator, I get this. And I want those numerators to be equal to, when I add these two together, I get this equation in the numerators by comparing the numerators. Well, what does this mean? I actually have two equations. So as plus bs is s. I compared the s terms on both sides. And then I have this minus 1 has to have come from the constant terms, a minus 2b. And so we have a system of equations. Well, I don't need these s's. Right. A plus b is 1. The coefficients have to be the same on both sides. Okay, so what does this mean? Well, there are many ways of solving this. Maybe I'll subtract the second equation from the first one to cancel out the a's. So we get 3b equals what do we got? 2, which means b is 2/3. And this first one, a plus b equals 1, tells me that a has to be 1/3. Okay. So actually, what does this become here? It's 1/3 over s minus 2 plus 2/3 over s plus 1. That's L of y. Right. Now we're ready to take the inverse Laplace transform. And what do we get? So this one just becomes 1/3 e to the negative 2t. Did you remember that formula? So that's this one here. Okay. Inverse Laplace transform of 1 over s minus a is e to the at. And this constant just comes outside. Plus 2/3 times, what am I going to put here? Not e to the, I'm sorry, I made a mistake here. This should be a plus 2t, right, by this formula. S minus a, and that just becomes a. Right, so a is 2. And here a is minus 1, so this one needs to have the minus sign. Okay. And what do we have? We actually have a solution to the initial value problem right here. That's our solution to the initial value problem. So this is y of t. So notice that we sort of got the entire solution just all in one go. We didn't have one step where we find a general solution, then another step where we solve the initial value problem. We just got the solution to the initial value problem. Okay, so let's summarize a little bit here. So steps. Well, let's say the first step. Sort of break this into 3 parts. First step is to take the Laplace transform of the differential equation. Okay. And use the what I was calling the key formula to, well, what do we do with that? We use it to rewrite L of y prime, L of y double prime, etc. in terms of just L of y. And we get these s's as well, but that's okay. All right, what was our second step? Once we did that, we noticed that we should solve for L of y. That's an algebra problem. And then finally, we take the inverse Laplace transform. Sorry about that. We take the inverse Laplace transform to find our desired solution, y of t. Okay. And so to me at least, the amazing part of this is that, if we look at this, where are we actually solving the differential equation? It's sort of happening right here, right? When we're just doing some algebra to solve for L of y. And then we need to take the inverse Laplace transform to come back. So really what the Laplace transform is doing is it's turning a calculus problem, solving the differential equation, into an algebra problem. And so I tend to think of this with a picture like this. So say we start with an initial value problem. Okay, this is what's going on. We take the Laplace transform, and we have some sort of barrier here. And so this is the t domain. This is where we're starting, where t is our variable. And then this is the s domain, where s is our variable. And so how do you go back and forth? Well, you take Laplace transforms and inverse Laplace transforms. So we sort of take the Laplace transform here. And then what do we get? We get an algebraic equation. In in L of y and s. Right. Okay, and then what we can do is we can we'll just solve for L of y. That's an algebra problem, not a calculus problem. And so we get something of the form L of y is some function of s. Okay, and then what do? We come back to the t domain. Again, the way to get back is by taking inverse Laplace transforms, and we end up with a solution. This is the solution to the initial value problem. Okay, but we could also have just solved the differential equation, the initial value problem, directly. But that would be the calculus problem. This is the kind of problem we've been doing this whole course. But the Laplace transform is a way to sort of turn calculus into algebra. And this might be an especially useful thing if we come across a differential equation that we're not familiar with, we're not sure how to solve. We can always take Laplace transforms, do this. It might be a very complicated algebra problem, but it's still just an algebra problem. Solve for L of y, and then come back. So this is sort of the method in a nutshell. And what I'd like to do for the rest of this lecture is just a couple more examples. So let's do a kind of feel like doing a critically damped mass spring system. So let's have solutions that look like e to the something and t e to the something. I want to see where that t e to the something comes from. So let's solve this this one. 8y prime plus, I think I need to put a 16 there. And yeah, I need to tell you initial conditions. If you don't have initial conditions and you still want to use the Laplace transform, and I mean, I suppose you could just say y of 0 is y0 and y prime of 0 is some letter there, and then just solve with those parameters. Okay, what's our first step? Take the Laplace transform on both sides. Okay. So I'll just do this all in one go. Plus 16 L of y is L of 0. That's just 0. Though I'll write L of 0, just to emphasize that we do need to do this to both sides. Okay, L of y prime is s squared times L of y plus, using this formula right here. So it's actually not a plus, it's a minus. Minus s times, sorry about that, s times y of 0 minus y prime of 0. Then I have plus an 8 times, again I need to use that formula, so I get a s times L of y minus y of 0. And finally plus 16 L of y, and that equals 0. What's y of 0? That's minus 2. And what is y prime of 0? That is 9. Here's another y of 0. Minus 2. Okay, and then let's take all the L of y terms. So we have L of y times s squared plus 8s plus 16. Ah, wait a second. What is that? That's the characteristic polynomial, isn't it? So that's actually no accident that that's turning up there. Okay, so what else do we have? We have plus 2s, and then we have a minus 9, and what do we have here? Minus 2, which is plus 2, times 8, which is plus 16. So minus 9 plus 16, that's a plus 7. And this is going to equal 0. So now, we try to, again, do this all in one go. So I'll move this over, and so I get a minus 2s minus 7 over s squared plus 8s plus 16. Great. So I did both of the first two steps. That was pretty quick. So usually this third step, taking the inverse Laplace transform, that's the trickiest step. So let's do that next. I need the inverse Laplace transform. So first of all, let's write this denominator as s plus 4 squared, right? We have repeated roots. Minus 4 and minus 4. Then my numerator is this. And this doesn't quite look like anything in a table, but I do want to point out one formula. This one here, actually. If we have s minus a to some power in the denominator, right, then that's going to come from something of this form. But notice that the numerator just has to be a constant. That n is just, a number, right, related to that power. So I'm going to try to turn into this formula. However, I have an s in the numerator. And there's a typical way of getting rid of this s in this situation. You can do partial fractions, but I think if you do it, you just sort of end up with this again. I'm going to replace that s with an s plus 4. Same thing as the denominator. I can't change the problem, though. What did I do? I added a minus 8 in that wasn't there before. So I'm going to add an 8. And then I still have the minus 7. Okay. And why am I doing this? Because now I can rewrite this like this. Minus 2 times s plus 4 over s plus 4 squared plus 1 over s plus 4 squared. This is going to be something I can use that formula on. And this, notice that, I'm canceling the s plus 4s. So that's how you get rid of this s. Okay. Okay, so what do we have? We have minus 2 over s plus 4. That's going to be an exponential. And then this one, what's this one going to be? Do you see what that one's going to be? So yeah, again, this is L of y. I'm going to use this formula. Okay. So we need n factorial over s minus a. So my a is negative 4. Sorry, this became very messy. My a is negative 4, and my n is 1. Great, I already have that 1 there. All right, so let's take the inverse Laplace transform. And I get y of t is minus 2 e to the, what should I put? This is a mistake I made last time, right? But it's s minus a, and then I have an e to the at here. So a is minus 4, so e to the minus 4t. Plus, well, this formula just tells me it's t to the 1, right? E to the at. T e to the minus 4t. So a is, again, minus 4. Okay, very cool. And yes, this looks like a typical solution to a critically damped mass spring system, for example. Okay, should we do one more example? Let's do an example of an inhomogeneous second-order differential equation. So let's do one more example. Okay, let's solve the initial value problem. This example is actually going to basically cover almost every idea we've seen so far. So y double prime minus 2y prime plus 10y equals 34 e to the 6t. Y of 0 equals negative 2. Y prime of 0 equals 15. And I'd really encourage you to pause the video and take some time to try this example on your own. And if you get stuck, then you can play the video until the point where I talk about that, and then maybe you'll get unstuck, and then you can again pause the video, try to work through the rest on your own. Okay, so now I'm going to do this example. What's the first step? Hopefully you weren't stuck there. We're going to take the Laplace transform of the whole differential equation, including this right side, right? Don't forget about that. Here it really matters. So we have L of y prime, y double prime, minus 2 times L of y prime, plus 10 times L of y. That's going to equal the Laplace transform of this, right? 34 e to the 6t. I chose that 34 to make the numbers work out. Nice. Okay, and then now what do? We use the key formula, or formulas. These ones right here. These ones you will eventually just memorize as you do more examples. So what does this one become? It's so just this L of y double prime part, that becomes, by our key formula, s squared times L of y minus s times y0 minus y prime of 0. Okay. Now this part is going to become minus 2 times s times L of y minus y of 0 plus 10 times L of y equals 34 over s minus 6. That's the Laplace transform of this. Okay, y of 0 is minus 2. Minus, 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 so be careful about that. Y prime of 0 is 15. Okay, let's do this thing again where I collect all the L of y terms. So I have an s squared minus 2s. I'm expecting to get the characteristic polynomial again, so let's just check. Looks like I do. Okay, and then we have a plus 2s, right? Minus 15. This one we have to be really careful about. But it looks like we have a minus 4, right? That's going to equal this. Okay, let's now move this all over to the other side. Oops. Yeah. L of y times s squared minus 2s plus 10 equals, well, we have this, the 34 over s minus 6. And there are a couple approaches you could use here. For example, you can try to combine these fractions if you want. So you can try to make a common denominator here. I'm actually going to try to avoid that because remember, often when we get to L of y equals something, we want to take partial fractions anyway, which is sort of the opposite of finding a common denominator. But sometimes that is helpful, actually. But here I'm just going to leave it like that. L of y is, now I have to divide by this thing. So that's the same as dividing both these parts by that. So it's 34 over. You can see that this is starting to get pretty messy. But this is typical. Okay, we have that. And then we have a plus minus 2s plus 19 over s squared minus 2s plus 10. Great. So we are already at the final step, right? We did this part and that part really quickly. But now we have to take the inverse Laplace transform. And we actually still have a lot of work ahead of us. That's always the hardest step, is to take the inverse Laplace transform. But remember, our idea is just going to be to sort of whittle this down until we get a sum of terms that all look like they came from our table. Okay. Let's go ahead and do it. So let me start with this part on the left. Let's try to break this up into two fractions. So I have an a over s minus 6. We did an example like this last time. Plus, this quadratic here, it has, you can maybe see that the discriminant is going to be very negative. So this actually has two complex roots. There's no hope of factoring it over to real numbers, at least. So I'm just going to keep it all together. Okay. But then, remember, I have to put bs plus c in my numerator. I need a linear function there to be sure of, getting any number I want there, including that 34. Okay. Let's go ahead and do this partial fractions. So the way I do it is just find a common denominator. I need to multiply this one by this quadratic over itself, right? So this is my numerator. And then what do I need to multiply this one by? S minus 6 over itself. So I'll get bs plus c times s minus 6. And again, I want that to equal 34. I want the numerators on both sides to be equal. Well, let's go ahead and expand this all out. So we get as squared minus 2as plus 10a plus bs squared plus cs minus 6bs minus 6c. Right? I want that to equal 34. And don't be scared of this part, because it looks like we just have one equation and three unknowns, a, b, and c. But actually we have three equations here, because the s squared terms, those have to be the same on both sides. So a plus b has to be 0, because there's no s squared term over there. Right? So these two just have to cancel. Now let's look at the s terms. I have that one, I have that one, and I have that one. This tells me that minus 2a plus b, sorry, not plus b, that's the red one, plus c, minus 6b has to equal 0. Okay. And then finally, I have my constant terms, that one and that one. So 10a minus 6c has to equal, oh, not 0 in this case. That has to equal 34, because I do have a constant term over here. Okay, so now we have a system of three equations, and it's not as easy to solve as the one we had last time. But it's not too difficult either, because this first one, we can just say b is negative a. Okay, and then we can plug this in for b there. So the second one actually becomes, so instead of this minus 6b, we have, well, plus 6a. So that first equation is going to become 4a plus c equals 0. And then we have 10a minus 6c equals 34. Well, let's multiply this one by 6. And then add them, right? We have 34a, that's why I chose the 34. The c terms cancel. We get 34a equals 34, which tells me a has to be 1. Great. And then hopefully we can get the other ones pretty quickly. So if a is 1, well then b is negative 1. And c, oh, we can use this one here. C has to be negative 4. All right. Let's rewrite the whole thing. We have a brand new page. But I'm not going to rewrite this. I'm instead going to write this in this form. Okay, so L of y is actually a, which is 1 over s minus 6 plus bs plus c minus s minus 4 over the quadratic, s squared minus 2s plus 10. And then we have this one still. Don't forget about that one. We have a minus 2s plus 19. That's also over an s squared minus 2s plus 10. Well, we can probably combine these. That's probably not going to hurt. 1 over s minus 6 plus minus 3s plus 15. S squared minus 2s plus 10. This is looking a lot nicer, right? This first part I can already see is going to become an e to the 6t when we take the inverse Laplace transform. I'm not quite sure what this is going to become. But now I'm going to use my other typical idea for taking inverse Laplace transforms, which is completing the square. So let's complete the square here in the denominator. Well, it will be s minus 1, right? I need to take half of that number, s minus 1 squared plus something. But let's just do this out on the side. What is s minus 1 squared? It's s squared minus 2s, that's why I took half, plus 1. I have s squared minus 2s plus 10. This already accounts for one of the ones, so I have a plus 9. So I just rewrote this. That was completing the square. So let's make a note of that. And then we did a similar example to this in the previous lecture, but let's do it again. I'm trying to include as many examples in these last few lectures as possible. So I apologize if it's getting a bit tedious, but just want to do a lot of examples. So it just takes working through a lot of examples to get the hang of all the typical ideas that we're going to use. Okay. What do I need to do next? So remember the idea was this doesn't quite look like anything in the table because it's sort of becoming clear that we're going to use this, right? So that's what the denominator looks like. But I have an s minus a or a b in the numerator. Well, here I have a minus 3s plus 15. Even if we factor out that minus 3, which we can absolutely do if we want, we'll still have an s minus 5, not an s minus 1. So in order to remedy that, I'm just going to write an s minus 1, okay? It's a typical idea, just to try to make it look like the formula for cosine. But you can't change the problem, right? So I added a minus 3 there that wasn't there before, so I need to subtract that minus 3, and then I still have the 15. Now I'm going to split apart this fraction. This first piece is going to involve the s minus 1. Okay. And the second piece will just involve a constant in the numerator, which turns out to be a 12. Okay. Okay, I think I'm finally ready to take the inverse Laplace transform. Let's look at our table. Which one is it? It's this one here. These two here. So I have an s minus a, that's b squared. Okay, so I'm just going to make note of that b is 3 in my formula, a is 1. And this is going to be the cosine, the exponential times the cosine, right? There's an exponential shift rule that was going on there. Then this one will be the sine. But notice what I need. I need a b in the numerator. So again, b is 3, a is 1. I need a 3 in the numerator, not a 12. So one last thing I have to do. I'm sure you can see what I have to do now. I just need to put a 3 there. And I have a times 4 out here. Okay. Now we are ready to take the inverse Laplace transform. And we will just get automatically our solution to the initial value problem. This first part, e to the 6t. And then we have a minus, actually, minus 3. Sorry about that. Minus 3 times an e to the at, e to the 1t, times a cosine 3t, cosine b, right? And remember, this is b squared here, that 9 in our formula. And then finally, plus 4 e to the t, right? Sine 3t. Okay. So that is the solution to our initial value problem. That involved quite a lot of work, right? And most of the work, I just want to note, so like the actual solving of the differential equation happened right here. It was just right here. It was that algebra problem there, solving for L of y. All of this was taking the inverse Laplace transform. So that's definitely the most computationally intensive step. And you might be wondering, what's the point of this when, we already have a method to solve differential equations like this? Right? This is an inhomogeneous second order linear differential equation with constant coefficients. We've solved differential equations like that. And the answer is, this method can generalize. So, for example, we could solve third order differential equations, fourth order differential equations, higher order differential equations, many different types of differential equations that we haven't studied. And one really cool thing is that we can actually solve some differential equations involving discontinuous functions. For example, imagine we have an RLC circuit and we're flipping a switch on and off. That's a discontinuous function. It just so happens that the Laplace transform works really nicely with that kind of function. And we're actually going to talk about that in the next lecture.